So given the root of a binary search tree and given an integer k, we need to find the kth smallest value of all the values in the node of the tree. And this is indexed at 1, right? So for example, if k is equal to 2, we need to find the second smallest value in the tree, which in this case would be 2. If k is 3, we need to find the third. If it's 1, we need to find the first, etc. Now, how do we do this question? One way we can do this is we can traverse the binary search tree in an in-order fashion. So what does in order mean? It means we, given the root node, yeah, we traverse the left subtree of that node, right? Then that's recursively. Then we traverse the node itself, right? And then we traverse the right subtree, right? So in this example, let's try, and then whilst we traverse it, right, we can build a list. So an in-order traversal of a binary search tree will give us will give us the list in ascending order. It would give us the values in ascending order, and we know this because of the characteristic properties of a binary search tree. Because in a binary search tree, or the left subtree will be less than the node, and the right subtree would be greater than or equal to the node. So that is how we know that this would give us an in-order traversal would give us the values in ascending order. So let's traverse this tree in example 1 whilst building a list. So we start, so we're given the node, right? And we need to traverse the left subtree. So we have to traverse this left subtree. So, and now we're going to be at 1, right? We need to traverse its left subtree. There is no left subtree, so we need to traverse itself. So we start at 1, then traverse its right subtree. So we're doing this recursively, right? This is just 2, there's only 1. Then, since we've traversed 3's left subtree, we start at 3, then we go to 3. Now, because once we've traversed the left, now we're at the node itself. Then we need to traverse 3's right subtree, which is 4. So yeah, so that's one example. Let's try another example. So now that we know that k is equal to 1, we need to return the 0th index, right? We need to return k minus 1 because in code this would be indexed at 0, obviously. So we need to return k minus 1. So that is the solution to this problem, right? Let's try another example. So in this example here, we need to traverse the tree in an in-order fashion, right? So whilst building a list, and this would be recursive, and it would, yeah, so this would be recursive. Now, how do we do this? So for this problem, we start at 0. We start at 5, which is the root node. And we need to traverse its entire left subtree, which is this entire thing here. And the first value of that is going to be 3, but we need to traverse its left subtree, right? And that leaves us with 2. So we need to traverse 2's left subtree as well, right? We need to traverse 2's left subtree as well, which leaves us with 1. And 1's left subtree, there is no left subtree, so we need to traverse the node itself, which starts at 1. So let's do 1, right? And now we need to traverse 1's right subtree. There is nothing there, so we move on. And since we've traversed 2's left subtree, we need to traverse it to itself, then traverse 2's right subtree, which is nothing as well. Then we need to traverse, since we traversed 3's left subtree, we traverse 3 itself, then traverse its right subtree, which is just going to be 4. And now we're left with traversing, since we've traversed 5's entire left subtree, we traverse 5 itself, then traverse 5's right subtree. And since k is 3 in this example, we need to return the second position in the array, which is k minus 1, right? And that's how this problem is done. The space complexity of this solution is the height of the tree, due to the space required in the recursive stack whilst visiting left subtrees and right subtrees. And on the worst case, the height of the tree could be like so. It could be very skewed, and it could be O of n. But on the average case, it'd be O of log n. But even on the average case, because we were creating a list at the same time, that is the length of the entire tree, right? So even on the best case, the space complexity is also O of n. So worst case scenario is O of n, best case scenario is also O of n, right? And then this time complexity is here, it's because we're visiting every single node in the tree, the time complexity is also O of n. To improve our solution, we don't need to visit every single node in the tree, and we don't need to build a list. So we could have a global variable 3, right? And when we do our in-order traversal, so the same traversal, we visit, so we start at 5, we visit its left subtree, visit 3's left subtree, then visit 2's left subtree. Now, once we visit 1's left subtree, which we can't, it's null, we visit 1 itself, right? Which is its node, and reduce k to 2. And here we'll return none, since we've not found what we're looking for yet, because k is 2. Now, once we're at 2, we return none to 3. We visited its left subtree, we visit it itself. We visit its right subtree, but there's no subtree, so we return none to 3, and we reduce k to 1. Then once we visit 3, we reduce k to 0. So once we know k is 0, we know this is our solution, right? We know that this is what we're looking for, and we can just return 3. We don't need to visit its left subtree. We don't need to visit its right subtree, and we can just return 3 to 5, and then return 3 as our solution. We don't even need to visit 4 or 6 in this scenario. So the worst case space complexity here is going to be O of n still, because we still need to, in this worst case, when the binary tree is very skewed, we could still have to visit every single node. But on average, it's O of k. And the worst case time complexity, which is still this case, is O of n. But on average, it's O of k, right? So on average wise, we've improved our solution. So let's jump into the code. We need to first initialize a global variable that everyone will have access to. So regardless of where you are in the stack, you're going to have access to this, right? And let's define a function, a recursive function, like a populate, let's say, let's do in-order traversal. Yeah, in-order traversal, right? And let's do this. Yeah. So we're defining our function. So if the node is none, so if we're in one of the leaves, so if the node is none, then, so basically the idea eventually is that we just want to return in self.in-order traversal, right? And that's going to be the root. Yep. Okay. So if the node is none, we need to just return none. Yeah, because if we go back to the diagram, you'll see that it's basically whenever whenever it's the root node. So this is a base case, right? Now we also need to call. So now we're at a node. So we need to see that we're at a node. So we need to call its left subtree, right? So we need to traverse its left subtree. Traversal. Can't spell in-order traversal. Let me just copy this. And we have node.left. We need to traverse its left node. And if the left node returned to us something of value, so let's say it didn't return none, but returned something that is not none, then we know that we've finally reached our position, our answer, and we don't need to traverse anything else, right? So we can just return our results, right? But if it is none, right, then we need to decrease k itself, right? So now we're at the node, so we need to decrease k by 1. And if k is now 0, if k is equal to 0, then, so let's say, for example, in the previous example, if k is 0, then we need to return 3, which is the node's value, right? But if none of that is true, k is not 0, etc., then we need to traverse. For sure, we know it's going to be in the right subtree, right? What we need to get is going to be in the right subtree. And that's what we do. So we're just going to traverse the right subtree. And if we submit this, we see that we got a good answer.